Hello everyone and welcome back to the MAE 52 virtual discussion series. This is session 8. With you again is Colin. Well, this session we're going to talk a little bit about FEA, or finite element analysis. So after we're finished modeling parts, we can do this kind of virtual testing of the part. Instead of having to build the part and physically test it and see how it breaks and learn from it that way, we can save time and expense by virtually testing the part. So in finite element analysis, essentially what it does is break the part down into small elements and treat those as little springs. And using the concept of F equals Kx, if you remember that from the equation for springs, Hooke's law, it then can determine what the stresses that develop in the part are from certain loadings. Now, we're going to just see a very simple example of this. This is an entire field, and there's an entire class that I recommend that you take. It's MAE 152 that goes over in depth about finite element analysis and how to perform these tests on your parts. We're going to see just a little bit about how to set up the part, how to load the part, and then look at the results. All right, with that, let's begin. When getting started with a simulation, it can often be a good idea to compare the results with a well-known example that has a good closed-form hand solution or good experimental results. In this case, we're going to use the cantilever beam. This beam is going to be fixed at one end with a load placed on the other end, on the free end. Our beam is 25 inches long with a rectangular cross-section that is 2 inches high by 1.5 inches wide. Now, looking at the equation for the maximum stress and the maximum displacement in the beam, we see the maximum stress is a combination of the moment, which is the load placed on the beam, times c, which is the maximum distance from the neutral axis or the neutral surface to someplace in the cross-section on the beam, divided by the area moment of inertia, which is described by the geometry. So let's take a closer look at this. In our case, we have a beam that is 25 inches long with a load of 100 pounds placed on the free end. We expect the maximum stress to be developed where the beam is connected to the wall or at the fixed end. Now, looking at this, the moment that's generating this stress is 25 inches times 100 pounds, or 2,500 inch-pounds. So that is our moment load on the beam. Now, due to the geometry of this cross-section, we see that C, or the maximum distance from the neutral surface to the furthest place in the cross-section, is 1 inch, or half of the height. Now, this will obviously depend on the type of cross-section you have. And then we see the area moment of inertia I, given by this equation, 1 over 12 bh cubed. Now, this is only valid for this rectangular cross-section. For different cross-sectional geometries, there will be a different equation for the area moment of inertia. So in this case, we have h of 2, or 2 cubed, 8, times 1.5, or 12, divided by 12. So we see that our moment of inertia in this case is 1 inch to the fourth. Putting everything together in this equation, we expect the maximum stress to be developed in the beam to be about 2,500 pounds per square inch, or 2,500 psi. So when we get into the software and we run the example, we're going to compare it with these numbers and see if our solution is valid. Now let's take a closer look at the maximum displacement in the beam. So the maximum stress here was only a function of the geometry of the beam and the load placed on it. The maximum displacement, however, has this material property E. So looking at this graph, this is a stress versus strain plot. E, or the Young's modulus of elasticity, is the slope of this linear region of the stress-strain plot. So this plot is developed by taking material samples and putting a load on them and pulling on them, measuring the strain versus the stress that's placed. Now, at some point, the material will start to permanently deform. This is called the yield point, and the stress at which this happens is the yield strength. So when we go into FEA, as we've mentioned, everything's basically based on F equals Kx, or Hooke's law. You can see Hooke's law here shown in a different way, which is stress equals E times the strain. And this looks very much like F equals Kx, where E is somewhat of the spring constant. This will be very important in our finite element analysis. Now we place E in here, and E is really where your intuition tells you that if I have this beam made of steel or I have this beam made of wood or plastic, that it will certainly deflect differently for the same given load and the same given cross-sectional geometry of the beam. And we get these from material data. Some of this is already in SolidWorks. If you have a different type of material, you can import these values as well. Okay, so let's take a look at this in the FEA environment. So we've modeled the beam already, and the first step to doing any finite element analysis is to obviously generate a model. Now, there's another step that you want to do, which is model cleanup. In our case, we don't need to do anything here, but oftentimes you'll have small details on the model that will not provide value to your analysis, but that will make it more difficult to mesh and possibly even have the simulation fail or give you erroneous results. So a lot of times you want to clean up the model. This can mean maybe if we had a small little extrusion here that's really not contributing to the strength of the beam, that we don't suspect to really compromise the strength of the part by it being removed. This will help it mesh better and obviously get more consistent results. So geometry cleanup is kind of the last step in geometry creation. So when it's time to simulate the model, what we're going to do is go to SolidWorks add-ins and select SolidWorks simulation. Once the simulation tab shows up, then we're going to select new study. Now there's a number of different studies to choose from. Right now we're going to be focusing on a static simulation. So we select static, press OK. Now we have this simulation feature tree or feature design tree. And we're going to go through this in order. So as we're doing any sort of simulation, we need to have this checklist. We need to have a material applied, obviously geometry created, but a material applied, boundary conditions applied. So this is a fixture and a load, or multiple fixtures and multiple loads. And then we need to mesh the part. This is where the part is discretized into small little elements where, like I mentioned, this F equals Kx really applies across these elements. And as this is solved, then we see the strains and the stresses developed in the part. After that, we're going to run the simulation. So let's get started. We have the beam, and we've already applied the material in the part space. We can change the material here if we wanted. Next, we're going to see connections. Now, connections are only going to be important if we have multiple bodies or we're doing this as an assembly, because what we're going to need to tell SolidWorks to do is how to treat the parts at the interfaces of the parts. Since we only have a single body here, we don't need to do anything with the connections. I highly recommend, at least getting started, to do the simulation on only single parts or single bodies until you're more comfortable and more proficient. You'll get better results. It'll be much easier to run. So even if we have this complicated geometry, we like to try to boil this down and kind of break it down into smaller subcomponents that really are, representations of beams and plates and things like that. Okay, the next thing is we need to apply a fixture, and this is certainly important. So we right-click on fixtures, and we see all the different types. In this case, we're going to select fixed geometry. And so we said that the beam was connected to the wall at this face, so we turn it around, and we hover over the face, and we see these icons show up on it. This is indicating a fixed boundary condition. We select. Now looking closer at these icons, it's a little hard to see, but there are 3 arrows and 3 discs, a disc attached to each arrow. What this is representing is that there are 3 translational degrees of freedom that are now constrained, they're fixed, and the discs show that there are 3 rotational degrees of freedom that are now fixed. In some cases, you will choose a set of boundary conditions where you won't have all 6 degrees of freedom fully constrained, and the arrows will show you that to try to help guide you and represent the boundary condition that you've applied. But we do want fixed geometry here, so we've applied that, and everything's good. We don't need to add another fixture. We press OK. Now the next thing we need to add is the load, and the load is applied at this other end. So we go down to external loads, right-click, and say add force. Now, we're going to select the face as the location for the load. You can see the default in SolidWorks is to make the load normal to the face. In this case, that is not what we want. We want the load to be vertical in the y-axis and pointed downwards with respect to this coordinate system. So we still select the face, but over here in the menu, instead of selecting normal, what we do is we say selected direction. Now, as we've seen a lot of times in SolidWorks, we give it a vector. And one of the easiest vectors to use is the normal to a plane. So in this case, selecting the top plane, the normal to this top plane will be in the direction that we want, in the y direction with respect to our coordinate system. And that has provided the vector we need to direct the load. So next what we do is we select the units. We'll select English, inch, pound, seconds. And then we have to turn on a force direction based on this vector that we've given it. So you can see there's three. This is direction 1, so that's still normal to the face, but really it's not normal to this face anymore. It's along the plane because we've given it this reference entity. That's not the one we want. We could give it this one, which is sliding across the plane. Now, this could be a way to load the beam as a cantilever beam, but because of our cross section and, in the absence of anybody telling you what's the way you'd want to load this beam, what would be the most logical, you can think in general for bending members that you want the tall side of the cross section to be basically parallel to the load. And if we look back here at the equation, you can see that the maximum stress, as I gets bigger, the maximum stress goes down, and certainly the displacement goes down. Now, because I is so sensitive to this vertical direction, it's h cubed, you can see that orienting the cross section in this direction has a lower maximum stress and a lower displacement. We could load the beam in this other direction where B would actually be the H, but you can see we'll get a higher stress and a higher displacement. So we're told explicitly here what direction we want to load the beam, but just for intuition building, in the absence of that, you want to kind of think, okay, the tall direction. You can think of something like an I-beam where we have the tall direction and the flanges on top. That is a really high moment of inertia. That's good for bending. It's a good member for bending. So this is not the direction we want either. We want this direction, which is normal to the plane. And that has the vector that we want. We're going to reverse the direction. And then, of course, we'll change the number to 100 pounds. Perfect. Now we have applied the load. So we go through our checklist. We've applied a material. We've applied boundary conditions, so a fixture and a load. And now we're ready to mesh the part. So to get started, we're going to right-click and say Create Mesh. Now we have this slider as a first cut to decide what size the elements are going to be. We do, however, have other mesh parameters where we can more fine-tune the size of mesh that we want. We can even apply a mesh control in local areas where we need to get mesh refinement just in a small part of our geometry. Now, we're going to stick with default here. In general, what you would do is you would run some sort of mesh independence where you do a few different meshes and you see, do the parameters change as you increase the mesh, right? As you increase the number of elements. Beyond a point where this curve starts to flatten out, that's where we no longer need to add more elements. We do have a problem here. In the case of our beam, right against the wall, the way we fixed it, we will get a stress that will continue to increase as we change the number of elements. This is, of course, not what we want. If you ever see this behavior, this can be indicative of a really sharp edge or reentrant edge where really the results can't be valid because as we change the mesh, the stress changes. We can almost make the stress anything we want by setting the number of mesh elements to a certain value. This is, of course, a numerical artifact, but sharp corners are oftentimes not good in a real structure. So we want to try to avoid those when we can. And in this case, just for our example, we're going to leave the mesh at default. But again, this is behavior that you want to watch out for as you're deciding the mesh elements that you need. In general, you want them to be small enough so that they can capture the geometry of the features on your part. And we want to look for badly shaped elements. So all of these look pretty good. These are tetrahedral elements. They're like little pyramids. And we want to look for ones that are really long and skinny. So these are okay. Everything in here looks pretty regular. But as we had different features, maybe we had circular cutouts, you'll notice that some of the elements may be badly shaped in those areas. That would be an indication that we need to either apply a local mesh control or we need to increase the number of mesh elements. Now, increasing the number of mesh elements makes the solution take longer to run. So we don't want to arbitrarily increase the number of elements. We want to do so in a reserved manner and adding just as many as we need to capture the physics of the part. So now we've applied the mesh. We see the part is now discretized. It's ready to run the solution. So we're going to press Run Study. Now, the first thing you want to do when you get the results is make sure, did it deform in the way you'd expect? So if the beam had been kind of crushed, that would be our indication, oh, we didn't apply the load in the correct way, for example. Maybe we still kept it normal to that face. We wanted to change that. But so far, we see that there's no deflection where it's fixed. There's the maximum deflection where the load is placed. This seems like it deflected in the way we would expect. So now we can start to look at the results. This is the maximum stress. And you can see that under the results folder, the stress is the one highlighted. So this color heat map is applied to the beam, showing us the value and where it's located in the part. We can change the units on this if we want by right-clicking, going to Edit Definition, and under the Definition tab, we can change this. We'd probably want to leave this in von Mises stresses most of the time, unless otherwise desired. But we can go ahead here and change this to PSI to compare it to our results. So now we see that the maximum stress developed in this was 2,564 PSI. We are expecting 2,500 PSI. So the results are pretty good. And as I mentioned, changing the mesh would change this result. And we can see that this maximum stress is located where the part is colored red. And we can see this is near the fixed end where we would expect. Now, if we double click on displacement, it now shows a different color map indicating the displacement results. We can again change the definition if we wanted to get a different unit system, but we see that the maximum displacement occurred at the free end, which again is where we would expect. If we needed to see any other results, we can right click on this and make different plots. Maybe we'd be interested in a factor of safety plot, which would compare the maximum stress that we developed in our part with the yield stress of the material. And so it is very important to look at the yield stress and compare this with the results that we get. So we see here the yield strength is about 90,000 PSI, and we only saw 2,500 PSI. Our part was not close to yielding. If our part was close to yielding, the results start to break down, especially when we pass the yield point. So we have to be very careful that we always say something about how close our maximum stress was to the yield strength, so that not only can we see did our part fail, but really to see, are these results valid? Can we trust this finite element simulation? Now, as a last step for a good presentation, it might be nice to show a little animation of the beam under load. So what you can do is right click on the stress plot or the displacement plot and say animate. And this will show a cartoon of how the beam deflects when it's under load and how the stresses develop. Now, of course, we want to save this as a video so that we can put this as part of our presentation. What you'll want to do is press stop. Then you'll want to check mark save as AVI file, and then choose where you want this located, any other options. Once you check mark that, then you can press play again, and it will save the video of the part being deformed. And this, of course, just like we've seen with all our other videos with the exploded views and the assembly animations, we can then add this to our final presentation. Let's take a look at another example. In this example, I'm going to look at changing some of the boundary conditions, some of the fixtures. So far in the beam, we've seen a fixed boundary condition. But in this case, I've built a rocker. So the way this one will work is this will be really an axis that this part could rotate around. We're going to have an input force on this hole, and then there's going to be some sort of resisting restraint on this hole. Now, to set up this part, what I've actually done is I need to split this circular face into two pieces. So I've used the split line tool, as we've seen before, to do this. I've drawn a straight line, and then using the curves split line, I have split this into a front and a back half. And this will allow us to apply the load onto this face as if there was some sort of axle through this that would be pushing really on only part of the face. And this can be a technique that you use because if we were putting a restraint or some sort of load and we are grabbing the entire inner face, this would almost be like we're pulling in different directions. So you do have to be careful. For example, if we were to grab this inner face and then even tell it to have the correct direction, on this side, it would be pushing, just like we'd expect, but on this side it would almost be pulling, as if the axle was bonded onto the inside face. So by making the split line feature here, we can really just load up part of the face and give a more realistic boundary condition. I've done the same thing here to resist, basically, if there was another sort of rod through this and that it was resisting the motion by pushing up on this face. I have not done the same thing to this hole because we're going to treat this as basically an axle where this can rotate around. There's no need to split the face here. Also, I've put in these coordinate systems, these reference coordinate systems, so that we can apply what's called a bearing load here to give an even better representation of applying a load where near the edges, since it's tangent, it's really not carrying any load. So the load varies as it moves along the face, having really the maximum here in the center, again, to give a little bit more realistic physical scenario. Okay, so we're going to open up a new simulation. We're going to still do a static simulation here. All right, so we've set the material. It's a 6061 alloy. We don't need any connections. All right, on to the fixtures. So we're going to grab fixed geometry again, but I'm going to do something a little bit different. Instead of just leaving it as fixed geometry, I'm going to select advanced. Now under the advanced menu, you can basically specify amounts of freedom that you're going to allow. So on this hole, what we want to represent is we want to represent something that can only rotate around the axis that's represented by this cylindrical hole, but this piece cannot move either along the axis or radially across the axis. So what we're going to do is select on cylindrical faces. Then we're going to select this cylindrical face. And here's how this works. These toggle buttons that are grayed out basically mean that right now it has all the degrees of freedom. But as we start turning these on, if we set it to 0, we're saying we will not allow any deflection. We will not allow any motion in that direction. So the first one is in the radial direction. So we're going to turn that on and leave the number 0. That means that it cannot move radially with respect to the axis, which is what we want. Okay, the very bottom one is axial. Once again, we're going to turn that on, and this means, leaving it at 0, that it cannot move along the axis that runs through this hole. And you can see it by the arrows. The arrows are saying, okay, again, the arrow means that it's restrained in that direction, so it can't move radially, it can't move axially. But what we're going to do is we're not going to turn on this button that's a circumferential motion, and by leaving this off, it means that we are allowing a degree of freedom around this hole. This thing could rotate around the hole. Now, when you do stuff like this, you have to be careful, because if you don't restrain the model properly, you're going to get an error message when you try to run it saying that there's excessive displacement. It means that it's not restrained. Basically, this thing could just keep rotating, which is not what we want. But this is good for this particular location. We're going to add other fixtures that will help reduce the motion and the degrees of freedom. Okay, so again, we've left off the circumferential because we want this to be able to rotate around that hole. All right, now thinking about this, if we were to push on this hole and this was allowed to rotate, we would need some sort of restraint to keep this thing from just spinning around. So we're going to add another fixture. We're going to do a fixed geometry. But again, we're going to press advanced. And then we're going to select on cylindrical faces again. We're going to select this face. Now, on this one, we're going to again say that we don't want any motion in the radial direction. You can see how that's restraining it. It's basically keeping it from moving across this axis. And you can see pushing on all sides. This is representing if you had some sort of metal bar in here that this could push up against. Now, as far as turning on some of these other restrictions, such as an axial motion or circumferential motion, if we turn all of them on, this will be basically a fixed restraint. However, we may want to leave some degree of freedom to allow this part to move, expand along this. Sometimes by having too much of a constraint, you can artificially kind of stiffen the part and develop stresses where maybe those stresses could be relieved if this part was able to move a little bit or expand. So maybe initially we actually want to leave those degree of freedom. And if we get a problem, then we can come back and turn those on later. But so far, at least at an initial glance, we have restrained this enough because while this could try to rotate along this axis, by this not allowing any motion across the axis, we have restrained the part. Okay, so that's it for fixtures. Now we're going to put on an external load. And again, we want to push on this face. So what we're going to do is right-click on external load, and instead of using force, in this case, we're going to try a bearing load. So we select bearing load, and then because we've already split this face, we just select the side that we want to represent. Now, for the bearing load, we do have to give it a coordinate system, and that's why ahead of time I've put in this reference coordinate system. So we select the reference coordinate system to put in this box. We're going to select English units here. We'll put on 100 pounds, and we're going to put on 100 pounds in the x direction, which you can see on the coordinate system, the x direction is in the direction that we want to push on this. So the scenario that we're representing is that we're pushing from this direction. This piece would want to rotate about this axis, and then it's being restrained here. So you can see rocker arms and these type of parts in many different scenarios. Now, the benefit to using a bearing load is we can choose a sinusoidal or a parabolic distribution, which, like I said, it represents that right here near the very bottom, this doesn't really carry load. So the force that's being applied here in this direction is much smaller than right here. So it's giving, in this case, a sinusoidal distribution along this face, which should more accurately represent if we had a metal bar in here and we're pushing on that face, and how the loading would be distributed along the inside of this face. And again, we're really checking to make sure that we haven't selected this face because we don't want to be pulling on that. There's really no mechanism in this particular part that's pulling on that side of the face unless it was by chance bonded there, which we're choosing to not represent here. Okay, so that's it for the external loads. So now we're on to the meshing. So we're going to create mesh, and let's leave it at default setting right now and see what happens. Okay, so you can see that overall it looks pretty good, except there's some really thin elements. You can see some right here. We can see some other ones maybe on the faces and near the holes. Really where we had curvature, we didn't have a high enough mesh density to try to capture the curvature. So we got some longer, thinner elements. In general, we want to try to eliminate these. So there's a couple things we could do. The first thing we can do is just go back and change the mesh density to fine. We can see it'll take a little bit longer to run, right? And so what it's done is in some places where it didn't need a lot of elements, it's put a few more. And then of course, where we needed to capture the curvature, it has enough elements. Another thing that you can do is when you're creating the mesh, you can do some things like change it to a curvature-based mesh, or even better yet, you can apply a mesh control, and then you can have selected entities like certain circular faces where the mesh density is smaller in that area, so it can capture those features where we're having the problem, and then in other areas the mesh size is bigger. Now, for a first approximation, you may not need to worry about this. Again, with this number of mesh elements, it's just going to take a little bit longer to run, but the important part is to try to look and make sure you don't have really long, slender elements. So let's stick with this mesh density right now. It's just going to take a little bit longer to run. Okay, so we go down our checklist. We have a material applied, we have fixtures applied, we have loading applied, and we've meshed it. We should be able to run. So again, this will take just a little bit longer because we have a high number of mesh elements. So we can see the progress coming up here. All right, so the first thing, again, we want to make sure that it looks like it deflected properly, which it does here. We can animate it, get a little bit better picture. All right, so far that looks good. And we're really looking at this hole to see if any weird stress develops. So we're going to compare this with actually adding a fixture right here, and I'll show you the difference. So this looks pretty good. It's kind of what we'd expect, and we can see where the high stresses develop, of course, near where the restraint and the loading were, and then in these faces right here. But I want you to take a look at this hole. So this hole, we've left a circumferential degree of freedom, right? And so we see some stress developing here, as we might expect, but I want you to compare it with a different scenario that we're going to see right now. So what I'm going to do is change that fixture. So I'm going to suppress these, and I'm going to change that fixture to just a simple fixed geometry. So I was warning against this, and you can see why we went to the trouble. So right now this is a fixed geometry, no rotation, no translation, but we've left everything else the same. So we're going to leave the mesh the same, but we're going to rerun the result. And then we're going to look at that hole, and we should see a little something a little bit different. Okay, so if you take a look at this hole, do you see how the stress is now developed here? And really this part has become largely unstressed. Well, what's happened is basically this hole is now rigid. It's bonded. So when we're applying a load here at this face, the moment's actually being taken up here, right? So it's not transferring the load through the part the same way. And you can see how important it is to have kind of the right boundary conditions. Really, if we have a rod there and this could rotate around the part, by having a fixed boundary condition, this isn't representing the physics quite well enough. So we're going to suppress that, enable these again, and run the study. And this is a good example of over-constraining can often lead to erroneous results, like I mentioned, by just overly stiffening the part. See, the part certainly bends differently, and different areas get stressed. And so if you had constrained this improperly, you can see that we would have actually had a false result here, and we would have not really known where the part's getting loaded and where the part really has the potential to fail. Another thing that can be interesting to do just in the presentation is to show the mesh, right? This kind of has a feel that it's been run through an FEA simulation, and it helps you also to notice if you have really large gradients across the mesh elements, which can lead to a bad result as well. If we have across just a single mesh element a wide variety of color, that can indicate that we have too high of gradients and the mesh elements are not small enough to capture the physics. All right, let's look at another example. In this example, I've made something to represent maybe a car hood, a car door. But really the important thing here is it's a really thin piece compared to the rest of its size. So it's been modeled with surfaces, which seems very logical. And as we've seen, there's benefits to modeling things with surfaces. But then what do we do when we get into the finite element analysis? Well, one thing that we have to do is we have to define the thickness of the part. Because the surface has 0 thickness, it's going to require us to then provide a thickness for the part. So there's a couple ways we can do this. We can, of course, take the surface and go to the surfacing tools and thicken this and turn it into a solid body. So there's something important to remember. When we're trying to model this and trying to simulate this, we need a few elements across the thinnest direction. So in this case, if this was, for example, 10 inches and this was maybe 7 inches, but then the thickness was a 1/4 inch or 1/8 of an inch, to be able to capture the physics properly, we're going to need to have at least 2 elements across the thickness. So that means if this is 1/8 inch thick, then we need 2 elements. So each element would be about 1/16 thick or 0.0625 inches. Now we said that this is 10 inches. So we're putting a lot of elements along this direction that maybe don't need to be there to try to represent the thickness properly. If this is the case, there's another thing you can do. Another type of element that we can use is called a shell element. So what we're going to do is define the thickness in the program, and it's really going to apply elements just along the sheet and not represent that dimension. That dimension is going to be represented in the program, in the math. So to do that, we leave this as a surface. Then when we come into the simulation, what we do is we go to the shell manager. Under the shell manager, then we select the surface. So we can either select the surface and apply a thickness, or if we have multiple surfaces, we can use the shell manager to decide what to do for each thickness. We can apply different materials to each surface and the thickness. We can thicken them differently. But since we have just one surface, right now what we're going to do is apply a thickness, and we're going to have the offset be middle, which means it's treating the surface as the middle defining surface, and then it's applying material on each side. So depending on the geometry, this may change what the part looks like just a little bit for the simulation. All right, of course we need to define a material. And then once we've done that, we can do everything the same, apply the fixtures, apply the loads. Now, I want to have a specific scenario here. So what I've done is I've applied a fixed boundary condition along all the edges. So I want to rigidly restrain this. And then what I want to try to represent is somebody stepping right in the middle of this part. All right, so we go to external loads, and we apply a force. Let's say maybe 100 pounds. We pretend somebody has one leg on it and they're trying to step on this. All right, so we select the surface that we want to apply the load on. We select 100 pounds. Now, it doesn't look like it showed up, but actually it's just being represented on the bottom. So we see the arrows, we want to switch the direction. Okay, but the problem here is it's distributing this 100 pounds along the entire surface. And that's not what I want to do. I want to localize it in a specific area. All right, to do this, we actually have to go back to the model and apply a split line. So we've seen split lines used extensively to apply appearances and some of the surfacing techniques, but here we're using it to actually segment regions like we've seen in the last example with the rocker arm, and here to segment another region to apply the load. So we're going to get out of this, go back to the model, and let's try to draw the region. So we're going to insert a sketch on this plane, and we're just going to use a spline here. We won't make it too precise, but let's try to capture maybe a footprint. This is a pretty large footprint, but we'll just represent that area. Then we go to Features, Curves, Split Line. Using that sketch, and we'll select the surface, this face. You can see we now have a region. When we get back into the simulation, it will now allow us to apply the load just on this region. So we go back to the simulation. We keep the same boundary condition. Now you could also do split lines to represent a different boundary condition. If you had maybe a bolt and a washer, you can put circular split areas that are representing how the bolt tightens down on the washer tightens down on the surface, and that's really what's kind of the clamping action, and that's the localized region in which you want to restrain the part. All right, now we're going to go back to the external loads, do the force again. We'll select 100 pounds, but this time we're going to select just this region. And you can see now it's being applied in this area locally. We'll switch the direction. Okay, now we're going to go back to the mesh, create the mesh. We can leave this at default right now. All right, we look around the area, we see if there's any unusually shaped elements. Everything looks good. All right, so now let's run the simulation. And this is good because you can see that it has now locally deformed, and we want to look for maybe the boundary conditions being stressed a little bit, but certainly kind of a smooth transition of the load outwards. If we see any sharp interface, we want to go back and look at the number of mesh elements we have, the way we've restrained this, and the way we've loaded this. As always, we can show the mesh, and we can look and see if there's any large gradients across any mesh elements. This might warrant a little bit finer mesh density. Again, it's really not a problem here because we've used this as a thin surface and we're using shell elements. We can turn up the mesh elements here without it causing too much extra time in our simulation to run. And we'll see if that looks any better. So this is an easy way to represent some unusual scenarios, and a lot of parts and a lot of projects may want to run kind of a localized load, and so this can be a really easy way to do that. Of course, you always want to animate it to see if it deforms properly, and this is a nice thing, again, to add into presentations. Another important simulation to look at is a frequency or modal analysis. So everything vibrates, and when we have machines and we have top-level assemblies where it has machine components in there, especially things that rotate, we can have problems where parts of the structure vibrate near the frequency that these components rotate at. If this happens and they're too close, what can happen is energy is pumped into the system and the parts can vibrate and oscillate violently and fail. And this can be a significant mode of failure. So we want to analyze the structure to see what are the natural harmonics or the way that the frame or our structure vibrates and compare these to these mechanisms that we have in our assemblies and make sure that the frequencies don't line up too closely. So we're going to go to New Study, and this time we're going to select a frequency analysis. Okay, now in the frequency analysis, what's interesting is you can apply a fixture or not apply a fixture. It's one of the simulations where you don't necessarily need a fixture. But if we choose not to have a fixture, then we need to change the number of harmonics that we're going to look for. So what I want to pretend is this is some sort of frame. Maybe it's a multi-rotor frame. I've applied these weight at the end to make it represent a motor. But the main thing is we need to decide, are we going to fix the center section or let this thing vibrate free in space? If we want it to vibrate free in space, what we're going to need to do is right-click on frequency, the very top of our simulation feature tree, go to Properties, and we need to ask for more than 5 frequencies. And the reason is because we have 6 degrees of freedom, 3 translational and 3 rotational. If we don't provide a restraint, then the first 6 modes will just be these rigid body modes. You can imagine something in space that I could rotate and push. Those will be the first ways that it thinks it's going to vibrate. Those are not useful to us. It's going to be any modes after 6 where it's going to show how the structure is actually vibrating. So in the absence of a fixture, we're going to need more than 6 modes. So let's put 12 here. Press OK. All right. Once again, we need to apply a material, or if we have different bodies, we need to apply multiple materials. We don't need a connection. In this case, it's a single body. Now, in terms of fixture, let's first simulate this with a fixture, and then let's simulate it without a fixture. So I'm going to say Fixed Geometry, and let's just go ahead and restrain this top and bottom surface. So now, because of the fixture, we've restrained these rigid body modes. So even our very first harmonic that we get is going to show vibration of the structure. But when we do the simulation again and take away this fixture, then we'll see the difference. Okay, we don't need to apply a load. In this case, we can, but we don't need to apply a load just to see how the structure is going to vibrate. Of course, we do need to mesh. So we'll say Create Mesh. In this case, I'll dial this up maybe just a little bit because I have some fillets, some radiuses here. So there's the part meshed, and now we're ready to run the simulation. Takes a little bit longer because I have a number of different mesh elements here. Okay, great. So you see under the results, now instead of seeing stress or strain or displacement, what we see is something called amplitude. So this is representing the different frequencies in the way the part vibrates. Again, because we have the restraint, even our first 6 are showing how the part will vibrate. They're not rigid body modes. So something important to note, even though we have this color map that shows amperes, which it's leading you to believe that this is the amplitude of the vibration, this is not true. You can't really use this to ascertain what the amplitude is going to be. What you really get, the valuable information that you get here, is what the mode shape frequency is. So it's saying that to get this mode shape, it's vibrating at about 250 hertz. So if we had something spinning, parts of an engine on this structure that was spinning at 250 hertz, then we would potentially excite this mode. And if we right click and say animation, we can see what that looks like. Especially in the frequency analysis, I think it's very valuable to look at the animation to see really how the parts are vibrating. Of course, we can go through them. So this is mode 2, and we'll just animate that one. So right here we have these arms moving up and down, specifically this one, and we can see this one is also close to 250 hertz. We can click through them. So we have a number of different modes here that are all near 250 Hertz. In the case of our part, it would be a very bad idea to have this located with any machinery that is operating near that frequency. We would have the potential to really damage this part. Now you can see that after we pass a certain amount, now the higher harmonics are certainly at a higher frequency. Now let's go ahead and remove the fixture and see if it vibrates any differently. So I'm going to suppress the fixture. Now it's just vibrating in free space. We'll run the study again. Okay, so now you see that for mode 1 has a frequency of 0, mode 2, 0, mode 3, and so forth. These are all really close to 0. So the first 1, 2, 3, those are the translational degrees of freedom. And then 4, 5, 6, these are the rotational degrees of freedom. So again, those are rigid body modes. They do nothing for us. They're just there because we needed to ask for 12 harmonics. So 7 through 12 are going to show the vibration of the structure. So you can see here, it's a little bit differently. So in free space without that fixture, now this mode, the first mode that we encounter, vibrates at 230 Hertz, and it looks a little bit different. And of course, as we go through, some of the modes look similar. The frequencies have changed a little bit. So by having the part restrained versus unrestrained, it does vibrate differently. And that makes sense if you've played with anything that vibrates, holding it against a solid surface maybe, and then vibrating it, or kind of understanding how it vibrates in space. But again, this frequency analysis is extremely important, especially when you're considering components that you expect vibrations in your part or that have other machinery, because again, everything vibrates, and this can be a critical failure if you're not careful. All right, we've now seen how to perform a basic simulation in FEA and in this SolidWorks FEA environment. So remember, the first thing we need to start with is our geometry. So if we have a large, complex part or assembly, we often want to figure out how to extract a part of interest. So maybe if we had a car, for example, and we're interested in the suspension, maybe we want to try to extract just a single rocker arm and do the simulation on that. We'll have a lot better results. We'll have a lot easier time getting this to work, especially at the beginning while we're learning this. The next thing we want to do is ask ourselves, does the geometry need any cleanup? Oftentimes, you may even need to make a special part that represents the part you want to test, but that's made specifically for a simulation environment. So in the case of this beam, this cutout at the back near the fixed end would certainly contribute to how this beam develops stress and how the beam behaves. In this case, we would not want to remove this particular feature. Now imagine if we had some small holes up here or small extrusion on this face. This is likely not to contribute significantly to the behavior of the part, especially here near the free end. If these parts are small enough, it may be worth taking them out and cleaning up this geometry so that we get a better, more consistent mesh and the simulation runs faster. Now, after we've done the geometry cleanup and applied a material, we need to ask ourselves, how should we fix the part? As we've seen, we can have the tendency to over-constrain and basically over-stiffen the part by adding fixtures. So we want to be careful to try to add a fixture in the way where we can capture the physics of the situation. And we've seen using things like split line to get different faces, and how we can change the fixtures to allow certain degrees of freedom while restricting others can be very valuable to capture the physics in the way we want. The next thing we want to do is apply an external load, and we've seen there's a number of different ways we can apply the load, specifically how we can change the direction of the load, whether we need to isolate it in a small area using things like split lines to have just a small region, or even something as simple as attaching it to the face in this case, but directing it instead of normal to the face in this case downwards, but in the direction that we want. After that, we need to mesh the part, and as we've talked about, this is where we're really capturing the physics. We're taking this kind of continuum or continuous piece of material and breaking it up into small chunks so that across these chunks we can try to capture the behavior. Now, of course, we want to look for badly shaped elements, especially near things like small features and curve features. And if we feel that this needs more mesh elements to try to recreate the part better, then we'll increase the mesh size. But of course, this comes at the cost of simulation time to run. Now, after we've gone through our checklist and looked at we have a material, we have fixtures, loads, and a mesh, we can then see how does the part behave. Of course, every time we run a simulation, we want to compare the yield strength to the maximum stress developed in the part. If the maximum stress developed in the part is too close to the yield strength, the FEA results may not be valid anymore. Not only, again, if we get close to the yield strength, may the part actually start to be failing, but the FEA results break down in a linear static analysis. So we need to be very careful, and we always want to we want to address how close our maximum stress is to the yield strength. Of course, we can look at the menu and change any of the units that we need. We can show the mesh if we're curious to see how the stress is developed in relation to these mesh elements. If we have large color jumps across the elements, it may be another indication that we need to refine the mesh a bit. But I hope this helps. Simulation is a very valuable part of computer-aided engineering, and now that we've learned how to create parts, we can simulate them and help our development and ultimately build better parts and products. All right, thank you again for watching.